Okay, in this equation, I've got a cylinder, 20 pounds. Okay, it's pushed against a spring. This is not a linear spring. Okay, the spring has a force given by this equation here. Okay, so I push against it, compresses 0.05 feet. Okay, and I want to determine the speed of the cylinder right as it gets back to zero. Right when it kind of pops up and gets full extension or back to neutral, I should say. Okay, so again, my equation here is going to be my initial kinetic energy plus all of the work being done equals my final kinetic energy. Okay, my initial kinetic energy, of course, is going to be zero because I guess, it starts from rest. Does it say that? It's the assumption you push it against and let go of it. Now, what I'm working for here is the work being done. Okay, so all I have here is I've got 20 pounds straight down, and then I've got the force of the spring right back up. Okay, so let's start with the work due to gravity, right? And that's just going to be 20. Okay, and its motion is going to be 0.5. So again, remember, I start with it compressed. This motion is upward, right? I'm pushing it up at this point, right? I compressed it, let go, and I want to figure out right after it gets fully extended what's going on. So it's pushing it up. Motion is upward. Weight is downward. So this is going to be a negative work. Okay, now the spring's going to be doing positive work, again, pushing it up in the direction of the spring force. Okay, so I'm going to have plus. Now, this force is not a constant force, right? So I have to use my integral, right? My work, remember, is FDS in general terms, right? So I'm going to take the integral, okay, where the force as a function of s is 100 s to the 1/3 ds. And again, this occurs from 0 to 0.5. Okay, and that's a positive work again because the spring is in the same direction as motion. That spring force is in the same direction as the force. Okay, so you have that integral given right there. Okay, so from that, that's all the work being done. Work of negative work of gravity, positive work of the nonlinear spring that I have there. From that, I can then find my kinetic energy at the end, which is 1/2 times 20 over 32.2 times the velocity squared, which is what I'm looking for. So piecing this all together, I get 0. The work being done, once I calculate that integral, and I'll let you do that on your own, I get 3 point, or I said 0.3815. Okay, also taking into account that I've got that negative weight going on there. So I've got that force of the spring that I calculate using the integral of FDS. Okay, where F is a function of S, and you calculate that out. Okay, and then set that equal to the final kinetic energy, which I get to be 0.31056 v squared. And I can very easily find that v equals 1.11 feet per second. So again, with this one, we have a nonlinear spring. So we kind of have to go back to the base equation for work, which is FDS, perform that integral for that nonlinear spring, knowing how the spring behaves relative to the compression in that spring. But then once I have that, I can very easily apply that, find the work, set that equal to the final kinetic energy, and determine what the velocity would be once that thing is extended again.